Okay, welcome, Mary Chan, Sarah, Megan. Thanks, Braulio. Um, Let me jump in and talk about the plan today. Okay, the plan, as usual, is I'll start out with Q&A. And I want to mention, especially, I mean, it could be about anything, but my guess is most of you right now are focusing on the project. So I'll talk about the project also, but so this is a good time to ask questions. And then after that, we're kind of changing gears a bit. We have been spending the last 3 or so weeks, actually 4, I think, really talking about the mean and or proportions, whether you have a quantitative question or a yes/no question. Now we're going to move into a different kind of survey question. What other kind of surveys could there be besides quantitative or yes/no? So what's another type besides a yes/no or a quantitative? Because that's what this week is all about. Y'all jumping in? Happen a lot. Any thoughts? All right, well, if you don't know for sure, you could have a qualitative survey question. You could have a question that's not yes, no, but still qualitative. So you could have a question, I don't know, such as what state were you born in? Okay, it's not a number. It's not yes or no. It's an, for me, it's California. Okay, or you might have a survey question such as what is your ethnicity? Again, not a number, not a yes, no. There are many, many type of survey questions that are qualitative. What is your major?
You have extra mass?
Huh?
Okay.
Oh, let me mute you. There we go. Yeah, and unmute yourself if you want to talk. Just to let you know. So we're talking about qualitative survey questions. So we're going to be looking at hypothesis testing. You can't really do a confidence interval when it's qualitative. It doesn't even make sense. But we'll talk about a certain kind of hypothesis test for qualitative studies. And we're going to start out with the distribution that allows us to do that, which is called the chi-squared distribution. I'm not going to get into the mathematics because actually it's really intense. So we don't do that. I'll show you a picture of it though, and play around with it and let you know that it is the distribution to use, and it's called the chi-square distribution. Then we're going to be looking at what's called the chi-squared goodness of fit test. And a chi-squared goodness of fit test is when you know a population distribution and you want to say, is your population that you're interested, sometimes a subpopulation, for example, does that have the same distribution? Okay. Or maybe you want to say, is your distribution normal or is your distribution uniform? That we're going to be using the chi-square goodness of fit test. Then after that, we'll get into the chi-square test for homogeneity. Independence. And that is when you have 2 qualitative survey questions and you want to find out if one is independent of another. We already talked about independence in chapter 3, but only for a very specific, item in, the answer, this specific answer independent of this other specific answer. Here, we're going to be looking at just the 2 things independent or not in general. Then we'll look at chi-square test for homogeneity. And that's when you have 2 unknown distributions. So maybe you're going to be looking at, a difference between in-state and out-of-state people. And you want to have a qualitative questions and say, well, are in-state and out-of-state any different from each other? Okay, and that is going to be a test for homogeneity. So that's the plan for this webinar. Are there any questions? And again, this is a good time to ask questions. Any questions at all?
Just a quick question, Larry. For last week review for dependent variables, with the dependent variable, the like you dependent one and then U2, is it always compared with 0?
That's a really good question. And so the idea is, at least, so for our class, remember the title of the class is Elementary Statistics. That's the first thing. So in the real world, could it be compared with something else? Yes. Very rare for that to happen. So I won't ever ask you a question where you're going to compare it with something else other than 0. Okay, where you subtract and you get something different. But I'll tell you just right now, kind of maybe a situation that might happen. Let's suppose you're an elementary school teacher and you give a kind of a pre-test. Let's say you teach 2nd grade, and day 1 of your 2nd grade class, you give all your students a test. And then on the last day of class, you give them another test. So that would be like the one case where you don't want to see if they're the same. You want to see if they, you hope you're a great teacher and you hope that you have helped them improve more than 1 year of learning. Does that make sense?
Yes.
But almost all the time, other than like a few examples I could make up, you want to find out if they're the same or not. Does that make sense? So in our class, I'm only going to give you questions about being the same. And if your project, for some reason, you had something like that elementary school example, you're allowed for your project to do where the mu naught is something other than 0. I don't think I've ever had any projects where they did anything other than 0. Okay, and I've been teaching this for many, many, many years. Okay. Oh, I want to give you a heads up, possible bad news. I just got a big note that says your internet connection is unstable. So if you can't hear me, let me know. And if for some reason the internet dies, I'll try to get back on. So hopefully that doesn't happen. It's weird because the weather is beautiful. So it's not wind or anything, but hopefully the internet doesn't die. So if you can't hear me, please let me know because my internet says it's unstable. Other questions? Other questions? Okay, I want to mention, well, first thing, if you haven't already checked already, if you didn't see the notice, I finished grading today, this morning, and all the grades are posted for exam 2. So they should be up. You can look at them. You should be able to see my comments on all the problems that you had any errors on. If you have no errors, or if you leave it blank, I don't write a comment, but there's usually something I have to write. So you can definitely look at the comments, and again, pay attention to them because you have a final exam in, 3 weeks or so. So you definitely want to be, you don't want to forget this stuff. And it was, some did great, some didn't do great, kind of typical. So hopefully you were one of them that did well. So that happened. And then what is due on Sunday? What's the main thing due on Sunday?
Project 2.
Yeah, project 2. Okay. So you should have a lot of progress on project 2. And just like for project 1, if you send me your draft by Thursday at 8 in the morning, I'll look at it and give you lots of feedback. Okay. And if you send it earlier, then you'll get an earlier bit of feedback because I'll have more time. So just let you know that that's the day, that's kind of the deadline to send if you want feedback on your draft. A couple more things, because I mentioned it, but I want to emphasize it. The projects are not supposed to read like homework or exams. So homework and exam, you have one sentence to interpret, to give the conclusion. For the project, we're talking paragraphs, and you're talking about how it's going to be used, not just what does it mean to have this conclusion, but what is going to happen because of it. And make sure that in your project, throughout the project, for whether it's a confidence interval hypothesis test, you talk about what decisions your client are going to make, and not just write down the definition, kind of the template form that I gave you for the exam. So that's a big heads up. Don't make it look like the template. Any questions on that? The idea is fully elaborate. Okay, and also throughout the paper, you're gonna be doing the standard error, talking about the standard error. And I'll be online a lot, helping out, other than when I'm teaching, I'll be answering or sleeping, of course. I'll be happy to answer questions about the project. I want you to do well on it and have a good project. Don't wait till the last minute. That's a big mistake. Any other questions? Any questions? Okay, if there aren't any questions, I'm going to go talk about chapter 11. And I want to let you know, kind of good news is that most people find chapter 11 one of the easier chapters. We do have the project due, but, and you might be tired from the exam. So I kind of lighten up a bit. Kind of towards the end, we lighten up a bit. So if you find today a little bit easier, that's great. Okay, you might not, but most people find it, a bit nicer. Okay, and especially if you understand hypothesis testing, because that's all we're doing. We're just doing hypothesis testing. So let's see if you can remember. What distributions have we learned about already? Give me a few names. Hint is there, I believe there's 4 distributions you already know about. See if you can remember one. Put one in the chat box at least.
Uniform distribution.
Good. Uniform was one of them. Good. Normal was another one. That was a biggie.
Binomial.
The 2 others.
Binomial.
Yep, binomial. And one more, and the hint is it's the very easiest of all of them to put in the chat box. Because you only need one letter. That's a hint. See y'all jumping in? Remember the T distribution? So T, sometimes it's called the student's T, but a lot of people just say T. So that was when you had a hypothesis test or confidence interval for a mean and you didn't know the population distribution. Population standard deviation is what you didn't know. And then you use a T, if you remember that. So today, none of those are going to work. So we're going to have to use a different one. And I promise you, you're not going to understand why at all. The only way you can understand why literally is become an advanced math major, probably graduate school, because it's pretty intense. But I do want you to know, first thing, what it's called. And the name of it is the chi-square distribution. So chi-square. Okay. Chi, by the way, is a Greek letter. If you're wondering what it is, that's a Greek letter. Sometimes I have to maybe I'll write it out just so you can see it so that you recognize it when you read about it and stuff. Looks like a curvy X. So that's what chi-square looks like. And then this is one of those you'll just trust me on, hopefully, is that there is a square that happens at the end. So one of the good things about the chi-square distribution is you never get negative numbers. So there is no such thing as a left tail test. There is no left tail. Because if you square all the values, there is no left-hand side anymore. Does that make sense? So here is a picture of a chi-squared, and it's a interactive picture of the chi-square distribution, which I created. I did a little program. And there's degrees of freedom. I don't know if you remember, but the T distribution has degrees of freedom also, depending on the sample size. For the T distribution, chi-squared is a little more complicated. It often depends on how many categories there are in the survey question. So for example, if you ask what state are you from, and you only ask, people who were born in a state in the United States, then it turns out that there's 50 states, subtract 1, you get 49. So just let you know that, depending on how many possible answers there are to the survey question, that's going to change the degrees of freedom. So this is a picture, and this is with degrees of freedom 9. And you'll notice it's maybe slightly skewed to the right. There is nothing below 0. So that's why notice it starts at 0 and then goes up. And there's no negative numbers to even look at because it doesn't happen. On the other hand, if you have more possible outcomes, it actually starts looking more and more normal. Okay, even though it's not perfectly normal, it's a little bit more normal. It's slightly skewed right still. On the other hand, if you change the degrees of freedom to much less, it's not even close to normal. It's very skewed, and it gets really weird when there's just 1 degree of freedom. It just flies on up. So that's the chi-squared distribution. We're going to be looking at a hypothesis test. And as hopefully you understand and you remember, whenever you do a hypothesis test, there's going to be a test statistic. So if, for example, the test statistic was 18, that would be right here. Then there'd be a p-value, and the p-value is the probability always of being greater than that number when you're doing chi-squared. So in that case, it's the area to the right of 18, and that'll be the p-value for a chi-squared distribution. Any questions in the picture before I move on to applications? Any questions? And as I mentioned, you only have to worry about right tail. There is no two-tail. There is no left tail. So one of the reasons why the chi-squared is one of the easier ones, the easier chapter, is that you don't have to think about less than, greater than, or not equal to. It's just always a greater than. Any questions at all on this idea? Any questions? Okay. If there's no questions, what I want to do now is I want to do these by example. I think really that's the best way. I mean, I could lecture generalities, but I don't think it would mean anything to you. So I think I want to do these by example, and I have some examples. And I'm going to start out with the first one here. And here's what it says. It says, in California, 39% of residents are Latino, 36% are white, 15% are Asian or Pacific Islander, and 10% are other races. Okay. By the way, do you think I made this up?
Yes.
What do you think? Or do you think this is a fact? I don't see y'all jumping in. Can you hear me? Because it says my internet connection's unstable. I want to make sure you can hear me. Are y'all there?
Someone said yes.
Okay. Someone talked and said yes?
Yeah.
Oh, really? I didn't hear it. Huh.
I said
okay.
yes.
Okay, it might have been my internet. Like I said, if I don't answer you, that means my internet just stopped. Okay, so I apologize for that, but I got an internet is unstable message. So please, if I keep asking, then that means that the internet did weird things. Okay, yeah, the answer is yes. I mean, is it true? Yes, if you believe Google, because I just went to Google. It was easy. I went to Google and I found the percents and copied and pasted and changed the wording a little bit to make it easier to read. And then did an other because I didn't want to go through such a long list that Google had. So I believe it. Sounds reasonable. Public Policy Institute of California is who published this. Okay, but here's the question. Okay, yeah, we got California, but what about college students in California, and particularly California community college students? And the question is the distribution of races different for California community college students? Because that might be something that people might be interested in. So a survey was done, and this one, I'm going to give you a disclaimer. Survey could be done. I just made up numbers. But a survey could be done of, let's say, 300 California community college students, and 125 were Latino, 92 were white, 33 were Asian or Pacific Islander, and 50 were other races. What can be concluded at the 5% level of significance? Any questions on that question? Any questions? All right, so the first thing you'll notice, and this is very important in this class, you should always think about the survey question. What's the survey question for this study? What's the survey question?
The distribution of races of different California community college students.
Okay, so that's a good idea, but that's not the survey question. And I'm glad you said this because I wanted to make sure that everyone gets the difference between the survey question and what the researcher is interested in. The researcher is interested in the distribution of races of California community college students. That's not what you're going to ask each individual student, right? I'm not going to go to you as a student and say, what is the distribution of races of California community college students? That's not the survey question. Does that make sense? So it's very important to know the difference. What's the survey question in this case? Very simple. It's a few words.
What race are you?
Yeah, what race are you? Any questions on that? So again, it's very important to be able to look at a question like this. It's not a trick question or anything, and be able to think about what are you going to ask each of these 300 students? And you're going to ask them, what race are you? Okay, or something to that effect. And then the person, the student, might say, I'm Latino. Okay, or I am Pacific Islander. Okay, and the point is that the answer to the survey question is not a number. It's not yes or no. It's a word. Any questions on that? Okay, and that means we cannot use any of the hypothesis tests we have had yet, because we only know how to handle quantitative data, number answers, and yes/no answers. So now we're moving to chapter 11, where we learn how to handle the word answers. So that's the first thing. Second is how, when we're doing hypothesis testing, once you've read the question, what's the first thing you always do after reading the question for every hypothesis you've done in the last few weeks? What's the first thing you write down? I'm looking for a symbol or two. Simple.
The null, H0.
Yeah, H0 colon. Any questions on that? Okay, and I want to mention something because I'm not sure what I can do to like bang it into your head that whenever you have a hypothesis test, you need to write H naught with a colon, because, and then you write what it's about. But a lot of you didn't write that part, or some of you didn't on the exam, and you lose points. So it is important to do that. And I also want to mention a big deal is that in chapter 9 and in chapter 10, how many words were there for your null and alternative hypotheses? When you write them down, when I asked you on the test to write down the null and alternative hypothesis, how many words were you supposed to write? And it says main internet is unstable, so say it a few times. So how many words were you supposed to write in chapter 9 and 10 for hypothesis testing? Very easy answer.
Only like one.
Even less.
Oh.
How many words?
So that would be 0.
0. Okay, so in chapter 9 and 10, you're not supposed to write any words down for H naught and H1. You're supposed to write symbols. Things like mu equals 4, or P is equal to 0.38. Okay, all symbols. Got it? The reason why I'm really drilling this down is that we're changing this week for this chapter. But again, in 3 weeks, you have a final. And I want to make sure that when I ask you questions from chapter 9 and 10, you still don't have any words when you're writing H naught and H1 down when I ask you for the null and return hypothesis. Okay, so promise me that you're not going to write any words if it's coming from chapter 9 or chapter 10. Okay, and by the way, some of you wrote whole sentences on the exam too, and that was not good. Okay, you were supposed to just have symbols. Chapter 11 is different. Chapter 11 is going to be all words after H naught colon. And here's the way we're going to write it down. And funny thing, when I asked you what the survey question was, I don't remember who said it, but basically you told me what H naught was. And that is the distribution, or let's go racial distribution for California Community College students is the same as what it is in California. Any questions on H naught? Okay, then we have H1. And the idea is once you have H naught, H1 is supposed to be very easy. So you're going to have H1. What's the only difference between H naught and H1? We've seen this before. Or the idea before.
Use different.
Yep, we could use different. And you have a couple choices. You could use different or you could use not. So I'm going to copy and paste. It's one good thing about doing things on a computer, including your exam, is that you can copy and paste and change what you need to do. Okay, and you could do different. It's less typing. Just put not right there. The racial distribution for California community colleges is not the same as what it is in California. Okay, you could also write is different from what it is in California. It's just more typing. Any questions on H naught and H1? And while you're thinking, I'm going to highlight something very important. And that's the word distribution. So I will let you know, this is a promise, you will receive points, or at least a point, for writing down the word distribution. Okay, so when you take the exam, that word distribution needs to be there if you're going to have this kind of test, which I'll talk about in a moment. Okay, and if you don't write down the word distribution, you're doing this kind of test, you'll lose points. So that has to be there. You get a note sheet. For the final exam, you get an entire page front and back of a note sheet. You got plenty of room to write this stuff. So write it so you don't forget and you get points. Okay, any questions on that? All right, the next thing to do, once you've kind of decided, sometimes you do it before you decide on H naught and H1, is what is the strategy? What test are we going to use? I'm going to let you know the name of this test. We will use the chi-square goodness of fit test. Okay, so that's what's called. Let me put this in red because it's kind of the important thing. It's the name of the test we're using. So we will be using the chi-square goodness of fit test. Okay, and this test sees or checks if an unknown distribution fits a known distribution. So in this case, the unknown distribution is the distribution of the racial distribution at California community colleges, whereas the known distribution is the racial distribution in California. Any questions on the strategy or the what test to use? Okay, and let me give you a heads up. Question number 1 on the final exam, and not just one, but it's, I think 1, 2, 3, 4, 5, 6, 7, and 8 are all going to ask, what test do you use? And you have to tell me which one. Okay, it'll be a multiple choice, and you have to click the right answer. So we've had a lot of different tests, chi-square test or confidence interval. We've had we're having a chi-squared goodness of fit test. We've had a test for 2 proportions. We've had a test for a single proportion. We have a test for a single mean. We've had an independent sample test for 2 means. We've had a dependent sample test for 2 means. We have a lot of different tests. And today we're going to do 3 more of them. We got another one next week, and we got another one the week after. So we're going to have lots of tests. We have confidence intervals, a whole bunch that we've already done. So there's multiple choices out of a lot of choices. And whenever you want to find out if the distribution of some unknown population is the same as a known one, that's chi-squared goodness of fit. Any questions on that? Okay, the next step in a chi-squared goodness of fit test is to write out a table. So we're going to do a table, and notice that for this example, we have Latino, white, we have Asian Pacific Islander, and other. So there are 4 different possible answers each person can give. Okay. And so I'm going to create a table which has 4 answers to give. And we're going to have what's called the observed and the expected. So I'm going to write it this way. So over here, I'm going to write Latino, white, then Asian / PI for Pacific Islander, and other. And then we're going to have what's called the observed. I'm going to use O for that, and the expected, which I'll use E for that. So stop me if there's anything you don't understand. And I'll get to explain what observed and expected are in a bit. But any questions on this table that I'm creating? Where have we seen tables before in this class?
Probability.
Yeah, probability. And it turns out, believe it or not, it's really the same. It's kind of a probability that someone's Latino or someone's white or someone's Asian or someone's other. And the idea is the probability that someone is Latino, Latino, for example, at a community college ought to be the same as the probability that they're Latino in California, which happens to be 39%. So really, this is the same as what we did before. But now we have observed and expected. Observed will be the California community college students we looked at. And those were 125 Latino. Then there were 92 white. And then there were 33 Asian Pacific Islanders and 50 other. Any questions on that? Okay, so that's what the observed was. That's how, when the study was conducted, that's how many people of each race were categorized there. Any questions on drawing the observed numbers? Okay, then come the expected numbers. How many would we expect to be Latino if the California community college system had the same distribution as in all of California? How do we figure that out? Any thoughts? Any ideas? And the key is it's kind of given to us, but it's given in a big paragraph. don't see you all jumping in. Okay, there were 300 students that were surveyed. If the distribution was the same as in California, then we would expect 39% of those students to be Latino. Any questions on that? And 39% of 300 is 117, if I did it in my head right. So I'm going to put 117 for the expected because that's 0.39 times 300. 36% are white. So we would expect 36% of the 300 to be white. And 36% of 300, 0.36 times 300, if I do it in my head right, is 108. Then 15% are Asian. 15% of 300 is 45. Okay. And 10% are other. 10% of 300 is 30. So let me stop. Any questions about how the expected counts were figured out? Any questions? Okay. Notice, for example, for Latino, did we observe what we expected? Are they the same? What do you think? What can you tell me? I'll let you answer. Hopefully you hear me.
They're not the same, but they're close.
Yeah, they're not the same. They're close, but close is a relative word. So we got to be careful about just saying close, but we don't want to say same either. So the question is, are they different enough to reject the null hypothesis? Okay, and you could look at the whites, you could look at the Asians, you could look at the others. None of them are the same, actually. But the question, are they different enough? And we're used to that for hypothesis testing. You have your expected number, like say, if H naught was mu equals 30, then your expected number is 30. And then you take your sample and you might get 33 for the average. And that's not 30. And you say, is that far enough away from 30 to be able to reject the null hypothesis? The same thing is happening here. Is we look at the observed, we look at the expected, and we say, are they far enough away from each other to be able to reject? And I'll just say it quickly, but you actually take the observed minus expected squared divided by the expected and add them all up, and that'll give you your test statistic. So you can just trust me on that one. You don't need to know all the formulas and equations because the calculator is going to do it for us. But I want to let you know that if the observed and the expected are far from each other, you're probably going to reject the null hypothesis. Whereas if they're close to each other, then you're going to fail to reject. Okay, same thing that happened before when we looked at means of proportions. If the hypothesized proportion is far from the observed proportion, then you reject the null hypothesis. It's no different. It's just a little bit more kind of messy with this stuff because there's multiple numbers and stuff. So any questions so far? All right. Hopefully you know what the next step is. What do you think it is? What's the next step? Because we've done this with hypothesis tests many times. Once you've got your H naught, your H1, you got your data, what's your next thing?
You find
Go into the calculator.
Yeah, we go to our calculator. And as you should be used to, let me go here. So here's the calculator. And are we towards the end of class or at the beginning?
The
Beginning.
Hopefully you all know that. That's an easy question.
end.
Yeah, we're getting to the end, so scroll to the bottom. Okay, we're not the very end. We still have a couple more weeks, but we're towards the end. Look towards the bottom and tell me which calculator to use. Because when I designed this, I put this in order at which we do things. So which calculator? Should be obvious. It's a little bit of a memory. I see y'all jumping in. Let me remind you again. It's in red. Chi-squared goodness of fit test is what we're using. So
it's 21.
21. So I hit 21. And then it says put in the observed and the expected separated by commas. So then if we look over here, the observers were 125.92. And then 33.50. The expecteds were 117, 108. And then 45.30. And I hit calculate. Any questions at all on using the calculator? Any questions? Okay, so you will notice when I ask you for the test statistic, okay, and by the way, remember I graded the exam, so it's fresh in my brain right now. I asked for the test statistic, and I meant it when on some of the exam questions, which means you need to write that down. In this case, the test statistic is chi-squared equals 19.45 is good enough. So the test statistic is 19.45. And the p-value, and actually let's write down chi-squared. And then the p-value was equal to 0.0002 about. Okay, and note, by the way, 19.45, if I go to that calculator, notice we're going to have 3 degrees of freedom for this one. $19.45 over here. And you'll notice to the right of that, how much area do you see under the curve to the right of 19.45? Just from the picture. Y'all see?
Close to 0?
Yeah, close to 0. Almost all the areas over here. So that's why our p-value, because the p-value is the area to the right. So that tells us that, we shouldn't be surprised that we have a p-value of 0.0002, very close to 0, which means that it would be very unusual for this to happen, okay, for what we observed to happen if the distribution were the same in the community college as it was in California. And when it's so unusual, that means we reject the null hypothesis. Any questions on that? And then what we can say, and one of the nice things about chapter 11 is the conclusion is very easy. Okay. And the conclusion is there is, what next two words? That we've been doing the last couple weeks.
Statistically insignificant.
Okay, the p-value is very small, very important. When it's very small, it's statistically significant. Otherwise, you're actually saying the exact opposite of the conclusion. Literally, it's the very worst mistake you could ever make when you're doing statistics is to say statistically insignificant instead of significant, because then you actually come up with the exact wrong conclusion. So very important to get that when the p-value is small, there's statistically significant evidence to conclude that. And now I can just copy and paste H1, change the grammar and the color maybe a little bit. That the racial distribution doesn't need to be read anymore. For California community college students is not the same as what it is for California. Okay. Any questions about using the chi-squared goodness of fit test?
Yes. So how do we know if the value is small enough, because we're not comparing it to a level of significance?
Okay, that's a good question. Look at the p-value, 0.0002. Have we ever had a level of significance less than that?
No.
So it's significant. So in the real world, no one's going to give you a level of significance. So that's why, in fact, I'm going to do the following. I'm going to write strong to really emphasize how low this p-value is. So in the real world, typically no one's going to give you a level of significance, but everyone understands what this p-value is. If you just state the p-value on a research paper, everyone's going to get it. Okay, because everyone, reading heavy research knows what p-values are and knows what it means to say p is 0.0002. So you will see in literature just the p-value. And sometimes that's it. They don't even write the next sentence because in literature and kind of the peer-reviewed stuff, everyone gets it at that point. We're at a community college, so I'm having you write the full sentence. But, in the real world, in the research world, you almost don't even have to write the sentence because everyone gets it just from saying the p-value. Does that make sense? Okay, so the p-value is meaningful. That's the big thing. Okay, and I want to also let you know that chi-squared tests, you're not going to see those like just reading, I don't know, CNN or something like that. You're not going to see them talking about a chi-squared test. Okay, this is done in research. Just let you know that this is we're not into the day-to-day kind of stuff. Now we're into research papers. So it's assumed that everyone understands p-value, and that's good enough. Any questions on that? Okay, so this is an example of a chi-squared test. This isn't the only one. And I want to let you know, I only have an hour or so, or hour and a half, or so. So sometimes I only have time to do one example of each main topic, but that doesn't mean there aren't others. I do other examples in the full-length videos that I've got, so you can see more. We'll see if I have a chance to do another one later, though, but I want to get to the two other topics. So any questions on chi-squared goodness of fit before I move to the next example? All right, so here's the next example. Okay, it doesn't matter what season a person was born when it comes to the type of car they drive. Okay, table below shows the season and car type. Okay, so the idea is, hey, if you're, I was born in the summer. So does that mean I might be more likely to have an SUV because I was born in the summer? Okay. Maybe someone else was born in the fall, and that might mean that they're going to have some other kind of car, like a, serious truck or something. Okay. And I do want to let you know, I made this up. So this is just an example, but this definitely, you can imagine doing a survey and asking people, when were you born and what kind of car do you drive? Be a very simple question. Any questions on this idea? Is this goodness of fit? What do you think? Is this a goodness of fit test where you're seeing if some observed distribution fits an expected distribution? Because what I found is probably the hardest part about chapter 11 is just knowing which test to use. Then the rest is all easy once you've got the test. Is this goodness of fit? What's your guess? The worst thing you can do is not guess. Hopefully my internet connection's working. So can we do this with a goodness of fit test?
No.
No, this is definitely not goodness of fit. There isn't an observed and expected. This is just 2 survey questions, and we want to see if you hear from one, does that help you understand the other one? That's all this is. Okay, this is very different than goodness of fit test. You can't do goodness of fit with this. Instead, we're going to use a different test, and it's called the test for independence, and it's still chi-squared. And it's called the chi-squared test for independence. And we use that when we have 2 survey questions that are both qualitative, right? When, what season were you born in? That's very qualitative. I was born in the summer. What kind of car do you drive? Very qualitative, not numbers, not yes, no. So there's 2 qualitative survey questions. And we want to see if they are independent. Okay, in chapter 3, I could have said, is being born in the winter and driving a sedan independent? And we learned how to do that, actually. I don't know if you remember that, but that happened in chapter 3. Now what we're doing is we're not doing a specific winter sedan. Now we're just saying season versus car driving or car type. So it's all of them kind of combined. And what you can't do is you can't just check to see if they're each independent one at a time. And, if you didn't get that probability of A and B equals the probability of A times the probability of B. Okay, there were 3 different choices. You can't do that because we're doing hypothesis testing. And when you're doing a sampling, instead of some theoretical distribution, when it's a sample, then when you have a sample, you're often off by a little bit. So you can't just check if those things are equal. What you really do is you want to check to see if those are far away from each other that you would say is too rare. And when we say far away from each other, when you have all these different possibilities, we got 12 different numbers here. Then there's going to be 12 different things to see if they're far away from the expected, and kind of average them out. And that's what the chi-squared does. Any questions on what this is doing, how this is different than the last one? Okay, so as you used to, we're going to have an H naught. And H naught and H1 are pretty easy if you remember the name of the test. H naught is that the season a person was born in and the type of car they drive are independent. And we have an H1. And I'm going to copy and paste, just like I did in the last example. But I have to change something. What do I have to change? What gets switched? Because H naught is not the same thing as H1. So how do I change H1?
Independent to dependent.
Yeah. So the nice thing with copy and paste is really easy. I just erase IN. And the season a person born in and the type of car they drive are dependent. Let me put those in red because those must be there. Just like when we talked about goodness of fit, you had to have the word distribution. For test for independence, you have to have the word independent for H naught, and you have to have the word dependent for H1. Any questions on that? So put that on your note sheet so that you don't make that mistake. Any questions so far? Okay, so this is a chi-squared test for independence. So the next thing we're going to do, what do you think? What do you think is next?
Calculator.
Yeah, we go to a calculator. So we're going to go to the calculator. And when we do that, it's not good as a fit. Whoops, that one. It's not good as a fit. We already decided that. So let's go back to the calculator menu. And which calculator is it? First thing, I better scroll a bunch because we're towards the end, getting even closer and closer each time. Which calculator?
$22.
Should be an easy question.
Test for independence.
Yep, test for independence. Okay. So when I made this, I tried to make it easy as long as you can identify the test you're using. Which calculator should be really simple. And now we're going to do test for independence. And this one, because there's multiple things, you got to have a table. So I made it with a table instead of commas. I had to make that decision, which was the better way to go. So I decided to make it look like the table. So let's go back and forth. And we have 73, 81, 76. And then 78. And then for the second, oops, not that one, 65, 68, 62. And then 64. And then for the third, we had 43, 51, 48. $43, 51, 48, 50. Any questions on entering the data into the calculator? So I scroll. Just hit calculate. Okay. What do you notice now? So what do you see? Here's a hint. Look at that p-value.
The p-value is close to 1 or high p-value.
There's only a couple here, so what does it tell you? Yeah, is it high or is it low? Take a look.
High.
Yeah, this is very high, actually. So our test statistic is 0.48. Our p-value is 0.998. Okay, so we have a very high p-value. When you have a very high p-value, what's the conclusion? So what's the conclusion when the p-value is so high? Yeah, you fail to reject. So there is not even close statistically significant evidence. So there is, I'm going to write insufficient. Evidence to make a conclusion that, and now I can just copy and paste. The season a person was born in and the type of car they drive are dependent. Okay, so we can't conclude. By the way, when you have such a high p-value, this is going to be important for your project, by the way. When you have a very high p-value, do you think it would be a good idea to just get a bigger sample size so that you can show that they're dependent? Or do you think it's time to give up? And again, this is very important for your project. Yeah, this is a give up. So you look at this, and one of the things you can say is that the standard error is definitely small enough. Your sample size was large enough to get a small standard error. So we really shed light on what's going on. Okay, if there's any dependency that's so tiny that it's not even worth noting. So it's a give up. The standard error was definitely small enough, and that's why we got such a big p-value. So that's just a note. You should always look at your p-value and think about, well, if you fail to reject, are you in that situation where you still might think it might be true and let's do a bigger sample size? Or maybe it's just time to give up. This is time to give up in a deep way. This is as big a p-value as you'll ever see, basically. Any questions at all about the test for independence? The chi-squared test for independence. Okay, and I will let you know that the mathematics behind this example and the other example, even though they're different tests and they looked a bit different, The math turns out to be the same. They're both using chi-squared, but that's something I just throw under the carpet because it's way too difficult to understand. Okay. And I want to mention one more thing. I'll show you in the first example, for example, is we showed that community college students don't have the same distribution. What we can't do is say, what's the reason why the distribution is different? Is it because there are more Latinos as a higher proportion, or maybe there are fewer whites, or maybe there's fewer Asians, or maybe there's more others? When you do a chi-squared goodness of fit test, it doesn't tell you which is a culprit on why we have different distributions. It only tells you the distributions are different. It doesn't say that it's because, you know, there's so many more others. You can't say that. Okay, if you want to be able to say something like that, and since we're getting towards the end of this class, I can start talking about this. If you want to be able to say something like that, then you need to take another statistics class. So not elementary statistics, you need to take advanced statistics, okay, or at least intermediate. Okay, you need to take an upper division or a graduate level stats class, and then you'll learn about how to analyze this in more detail. Okay, and same thing with dependent, independent. You know, if it's independent, if it's dependent, what makes it dependent? And that is more advanced stats. And we don't do that in this class. All we do is we just say there is insufficient evidence to make a conclusion whether it's dependent. Any questions on this example? Okay, let's do another example. And here's the next one. Do single men and women take the same type of vacation? So the table below shows the results of the study. Okay. And by the way, whenever I say results of study, what that usually means is I just made up a bunch of numbers. But you can imagine a study and you could ask a bunch of people, hey, when you went on your last vacation, did you go international? Did you leave the state, or did you just stay local? Okay, and go on a vacation in your own state. And you ask, and then you also say, you know, are you a man or a woman? Okay, and then if I had a big enough sample size, I can put in transgender or something like that. But with small sample sizes, you're not going to get big enough numbers for that. So I just stuck with men and women. Hopefully that's okay with you. And here's the results of the study, which I made up, but study could be done. And here we've got it. This one's a little bit different. Okay, because now we're comparing men and women. It's kind of like a mix between the goodness of fit and the independence, in that there's really kind of two survey questions. One is, in your last vacation, where'd you go? International, out of state, or local? And the other is, are you male or female? Okay, or trans, you know, you can do, or something, whatever. But the point is that there are two survey questions. So it looks a little bit like independence, but it's not. And the reason why it's not independence is we're not asked to see whether they're independent or dependent or they're related to each other. We're asked to look at men's distribution of vacations and women's distribution of vacations. Okay, and we're comparing the distributions between men and women. And that sounds a little more like goodness of fit. But with goodness of fit, you know one and you don't know the other. In this example, we don't know either. So it's kind of a mix of the two. And it turns out, and this one you're just going to have to trust me on, it turns out that you are comparing the two. So we're still talking about distributions. So we're going to use H naught. And that is the distribution of travel types are the same for men and women. Okay, which is different than saying gender is independent of travel type. It's different than saying the unknown is different than different distributions. And then H1, very easy. How does that change? I'm going to copy and paste. And what's the only difference? Yeah, take the same, turn it into not the same. Any questions on that? So the distributions of travel types are not the same for men and women. Any questions on this example? Okay, so now that we have that, we need to write down the name of the test. And the name of the test is going to be called the chi-squared test for homogeneity. We put that in red because that's the name of the test. I'm also going to put the word distributions in red because when I put it in red, that means it better be there on the exam where bad things happen to you point-wise. And if it is there, good things happen. Any questions at all on this one? And again, now it's a different test. Any questions? All right. So hopefully you're used to the next step. This is not a test for independence. So I'm going to go back to the calculator menu. And hopefully you can all tell me what calculator we're going into. Yeah, 23. And by the way, how many more do we have? Not supposed to be a hard question. Yeah, there's only 2 left, okay? We are almost done with this class, okay? So there's going to be 24 is next week, 25 is week after, just let you know that. So we're getting close to the end. So we're at 23, so I'm going to click test for homogeneity. And now there's an A and a B. A in our case is going to be the men, which is 29, 47, 33. $29, $47, $33. And then B will be the women. And the women were 38, 42, 36. Any questions on that? And hit calculate. And there we go. We got a chi-squared. We got a p-value. Chi-squared is about 1.4. P-value is about 0.5. Let me write test statistics so you know what it's asking for. And then the p-value is equal to 0.5. So when we have a p-value of 0.5, what does that tell you? Hopefully, you know, we've had enough hypothesis tests to be able to. So if the p-value is 0.5, what does that tell us? Yeah, we fail to reject. Yeah, we fail to reject. Okay, we fail to reject because we have a high p-value. So that means that there is a high, the probability of getting something as extreme as what we got is pretty high. So there's no reason to say anything weird happened, right? It's not unusual at all. When it's not unusual, you're saying, yeah, it's just business as usual. Men and women, they might have the same distributions. We don't know, but it could be. Definitely not going to say they don't have the same distributions. So there is statistically insignificant evidence to make a conclusion about whether or not the distributions, and now I can just copy and paste. Of travel types are, I'm going to say the same since I said whether or not, I can get away with saying the same. Okay. If you reject the null hypothesis, it's always H1. If you fail to reject, it's just you don't know whether it's H1 or H not. So whichever one you put, as long as you put the whether or not in there. Any questions on this idea? Any questions? Just a note, a language note. Homogeneity. You might have seen that word in English, not in math. Where have you seen something similar to the word homogeneity? Like homogeneous, it's a word. It's an English word. Yeah, homogeneous. And what does homogeneous mean? Yeah, same distribution. And that's why we call it a test for homogeneity. We're doing a test to see if the distribution's the same or if the distribution's different. Any questions on this example? So we now have from this chapter, we have 3 different types of hypothesis tests. We have the goodness of fit, we have the test for independence, and the test for homogeneity. Okay, and you got to get those straight. Okay, if you read the question and try and use the wrong test, things will not go well for you. So practice helps so that you can kind of figure out the right test and make it happen. Okay, and then once you have it, they all look kind of the same. And I do want to give you that big heads up again. I want to double the warning. Just because we have words for H naught and H1 in chapter 11 does not mean you're allowed to have words for H naught and H1 in chapter 9 and 10. Okay. And by the way, not in 12 either. So chapter 11 is special that way. One way I like to think about it is for chi-square tests, it's all about qualitative questions. Qualitative are the wordy answers. So wordy answers are going to have an H naught and H1. It's just a good way to remember it. Okay. It's not some mathematical reason, but it might help you remember. Whereas if it's not a wordy answer, if it's just a mean, for example, a number answer, then you're going to have only symbols. All right, we got some time. So let's do another example. I'm going to type one out. Okay, a study was done. Asking people how far they traveled. I'll do another travel one since we just finished the holiday. Okay, and I just read, it turned out this year's traveling was the same as last year. It was the same as 2 years ago. So we're back in terms of people traveling. So how far they traveled this Memorial Day weekend. All right. The mean was found to be 120 miles. And the standard deviation was 40 miles. I'm making this up, so don't quote me on anything. Okay, the table below shows the results. That's good enough. So we're going to have less than 80, then 80 less than x, less than 160, and x greater than 160. And what they found is that we're 56 that were less than 80. There were 61 that were in between 80 and 160. And there were 12 that were greater than 160. Again, I'm making these numbers up, so don't quote me anything, but it's important. So here's the question. Okay, and this is something we've seen a lot in this class already. Okay, on the exam, in fact, I asked it, I think twice on the exam, maybe 3 times, I think twice. So is the distribution normal? Okay, because we've talked about, assuming you have a distribution that's normal. Well, I never really told you how to tell other than you draw a histogram, you eyeball it, but eyeballing it is not statistically sound. Okay, saying I eyeballed it, it doesn't feel like it's normal is not something you can, that's not publishable. Now we actually have a way of at least looking to check for normality. Okay, and I will let you know there's actually a more sophisticated test that, as I've mentioned now twice today, is not happening in elementary stats. That would be advanced stats. Okay, and that's called the Kolmogorski test for normality. I'm not going into it, but what we're going to be able to do is test for normality with a chi-square test. Any questions? Any questions on the question here? All right, so if we want to find out if it's normal, what test, and the hint is it's going to be one of the 3 we've done today. Which of the 3 is it going to be? Is it going to be goodness of fit, independence, or homogeneity? It's going to be one of those 3. Which one? Better to guess than to not guess. On a test, if you leave it blank, I give you a 0. If you guess, you got a chance that you might get it lucky and get it right. So pretend like there's a test. So is this goodness of fit? Is this independence? Or is this homogeneity? So you should guess one of them. Best guess. I don't see y'all guessing. Remember, if you don't guess on the exam, you get a 0. Okay, homogeneity, good guess. But it's goodness of fit. So let me explain why. Okay, so homogeneity is when there would be two different populations or two groups where you don't know the distribution of either of them. Okay, well, we don't have two different groups. We're just asking people. It's just a bunch of people. Okay, and we want to find out if the distribution is normal. Normal is a distribution we definitely know about. We know everything about the normal distribution. We can draw a picture of it. We can do probabilities. We can do whatever we want with the normal distribution. So we're comparing a distribution we don't know, which is travel distance on Memorial Day weekend, to a distribution we do know, which is normal. So what I'm going to do now is I'm going to write down H naught and H1, then I'll put in the data, or more stuff. So H naught is the distribution, since it's goodness of fit, it has to have the word distribution, of travel distances during Memorial Day weekend is normal. Any questions on that H naught? Okay, well, I can copy and paste. Change the naught to a 1. And what's the only change in H naught? I mean, in H1. How do I change it? Yeah, is not normal. Okay, remember, if it's normal, that means you can do all the stuff that you know how to do, even if you have a small sample size. Although if it's not normal, you're out of luck. Okay, if you have a small sample size. So it's one way of like checking to see if it's normal, to see whether you need to make that assumption. And sometimes you don't, because you can just do a test. Now we got a test for it. All right, so now what I'm going to do is I'm going to write down, the first was the observed. Now I'm going to write expected. Now we got to remember, okay, these numbers are not random, this 80, 160. Okay, if you look at the 120 was the mean, 40 was the standard deviation. So 80 is one standard deviation below the mean. And if you remember, if you go to the left of one standard deviation below the mean, that was 16%. And that's because within one standard deviation was 68%. Outside is 1 minus that, that's 32%. So the left is half of that, which is 16%. And 16% of the sample size, well, let's see what the sample size is. So we had 56 plus 61 is 117, plus 12 is 129. So I'm going to take 129 and multiply it by 0.16. And I'll just pop it in this calculator. 129, oops, I'll do it here. 129 times 0.16. And that's 20.64. Let's call that 21. Better to round to the nearest whole number. And by symmetry, the right-hand side should also be expected to be 21. And then for the in between, the 80 to 160, that should be 68%. And that is about 88. Any questions on that? All right, now we're ready to decide whether we have a normal distribution or not, okay? Or at least conduct a hypothesis test. So let's conduct the hypothesis test. We have the calculators. We already decided this was a goodness of fit test. The observes were 56, 61, and 12. And the expecteds, 21, 88, 21. Oops. Let's try again. And I hit calculate. Is a p-value 4.4? What do you think? Is the p-value 4.4? Yes or no? What do you think? The p-value 4.4? What do you think? Be nice to get an answer. Okay. So this is where you got to be very careful. So I'm calling this out because it's a mistake people make on exams and other places, projects too. P-value can never be 4.4. P is a probability, and a probability can never be bigger than 1. So worry if you ever write down P equals and then you put a number bigger than 1, you made a mistake. You have to keep reading and see the E negative 16. That means move the decimal over left 16 places. So the P is absolutely minuscule. And in the real world, in literature, what you'll usually see is P less than 0.001. That's how people usually write it when it's a tiny, tiny, tiny p-value. They'll just write it that way. Because basically it's smaller than any p-value you care, any number you care about. It's tiny, tiny. And if the p-value is tiny, you say there is statistically significant. And I'm going to write strong. Statistically significant. It's strong because we have a very small p-value, not just like 0.03, but really tiny. Okay, statistically significant evidence to conclude that. Now I just copy and paste H1 and fix the grammar. Make that the lowercase. That the distribution of travel distance during Memorial Day weekend is not normal. Okay, and again, I want to let you know I made these numbers up, so you could do your own study if you wanted, and come up with these kind of things. But this is one way. Notice I didn't even have to look at a picture. I just do a chi-squared, and we can decide whether that we do not have a normal distribution. Don't even think about assuming it's normal because it's very much not normal. Okay, so that is pretty much everything I need to talk about for the chi-square distribution, chapter 11. And I want to doubly remind you, this is project week. That's where your main emphasis is going to be. Hopefully you'll send me your project ideas, your project draft before Thursday at 8 a.m. After that, I won't read it, by the way. I will look at the project 2 discussion board if you have any questions about the project at any time. I'm checking pretty often, each day. Oh, secret word. Thanks. Let me do the secret word. It's going to take a second. I got to I got to stop the share so that I can find it because I have a whole long list of them. Thanks. I almost got rid of it. Yep. Secret word of the day is distribution. Because if you don't have the word distribution for goodness of fit, or distributions for homogeneity, you will lose points on the exam. So it's important to have that word distribution. Let me make it bigger and brighter. Good, I spelled it right. So the secret word of the week 10, no, sorry, week 9 is distribution. And now I can stop the share. And let me stop the recording.